My name is FCRAR, and today I'm going to be talking to you a little bit about vision-based guidance and navigation for a swarm of small satellites and information flying mission. I'm a first-year master's student at South Dakota School of Mines Technology, and I worked on this project with my advisors, Dr. Hadi Fikramani and Dr. Randy Hu. So the things we're going to be talking about in this presentation. First, it's going to be CubeSats. So what are they? Why should you care? How many of them have been launched? Then we're going to talk about information flying. So why would we want to have multiple of these CubeSats trying to perform a similar mission? Then we're going to talk about vision-based pose estimation. So if we have multiple of these CubeSats in the same general area, they're going to need to try to stay away from each other or move around. So how do we estimate the relative locations? We're going to talk about dynamics and control. So how do we linearize orbital dynamics and then use that to control these CubeSats to be more efficient about how they transition between states? We're talking about distributed state estimation, so the difference between a distributed estimator and a centralized estimator and the strengths and weaknesses of each one of these. Then we're going to go into the future work. So what we're going to be working on this summer as well as in the next year. And then finally, open up the floor for any questions you may have. So first about CubeSats. So a general satellite, the Hubble Space Telescope, or a communications satellite is going to be about the size of a car. Hundreds of millions of dollars to produce. It's going to be hundreds of millions of dollars to launch as well. So that's completely out of budget, just unreasonable for any kind of small research group, or if you just want to perform so a small test, that's just completely out of scope for all those projects. So what we can use instead is called a CubeSat. There's a whole range of different sizes of these, but generally that's going to be a 10 centimeter cube with a mass of no more than 1.3 kilograms. And that allows you to be, it's a lot cheaper to launch because they're smaller, they're lighter, just a lot easier to produce in general for any kind of smaller experiment. One way to launch these is have them sent up to the ISS, where the astronauts can just sort of toss them off of the space station. And that's still going to be relatively expensive because there's only so much cargo that can go up to the ISS, and the astronaut's time is quite valuable. But if you can design your own launch system and try to use that, then you can try to put it as a secondary payload on a launch vehicle. So if there's a satellite or a launch that's going up to your desired orbit, then you can just try to piggyback off that, because your system is going to be very small, very light. So hopefully that would be a great thing to do. CubeSats have been relatively popular, especially since 2015. There have been over 1,300 launches so far, 1,200 successful deployments, and we're looking at about 1 to 200 per year recently. Then in the next coming years, it's just going to keep increasing. You know, we've got about 500 scheduled CubeSat launches each year, which is great. CubeSats are a great solution. CubeSats have many different areas of study, fields that can be worked on inside of them. So there's power generation with solar panels, power storage, the batteries. You've got the propulsion, and what kind of thruster you use, and the more efficient thrusters have a lower thrust. But then the field we're mostly working in, and mostly going to be presenting today, is guidance, navigation, and control. So how can we try to figure out where these CubeSats are, figure out what they should do? So one of the uses of CubeSats is we can take a large communication satellite that's got solar panels, it's got battery, it's got a communications antenna to communicate with Earth, it's got a couple of different sensors to measure the atmosphere, a couple of cameras, and a normal satellite. If any one of those sensors fails, there's really no way to replace it. So you've just got to live without that sensor, or you've got to replace the whole satellite, neither of which is a great solution. But if we could take each one of those subsystems and put that on its own microsatellite, then we could just try to replace that one. So we could try to get that to transport in place, and then it would be a lot cheaper than having to replace the whole system or work with a sensor that doesn't work anymore. Another thing is, instead of just having one large sensor, we can try to have 5 or 6 small ones to get a better average estimation. For some measurements, we try to create a phased array telescope where we have multiple of these CubeSats at a specific distance apart from each other. and try to create a larger subsystem with that. But in any case, if we're going to try to have these satellites be in a relative formation with each other, one thing we need is some kind of relative position estimate method. So that could be with a LiDAR, where we've just got a distance from the object. It could be with a sun or a star tracker, where that gives us a pretty broad relative position. But if you're near Earth, one of the good solutions so far has been to use GPS. It works just fine in space. A little bit of a better antenna, but it's fine. It's just fine. You get still 1.5 meter accuracy, which is just incredible. But if you're trying to do something that's going to need a lot better accuracy, like if you're trying to have these CubeSats flying much closer to each other, or you're going to want to try to dock them together at some point, then you really need a position estimate that's a lot better than 1.5 meters. So one of the ways to do that that NASA's already tested is called the Smartphone Video Guidance Sensor, SVGS. So they took an Android smartphone, just a cheap low power processor, cheap low power camera, and then they took what's called a 3U CubeSat. So it's just 3 CubeSats stacked on top of each other. And then they put some LEDs on there so that you can see it in the dark of space. And then they can get a pretty good pose estimate for this CubeSat with the camera. So it's low power. It's pretty cheap. Smartphones are quite cheap compared to satellites. One of the downsides of this system is that it's a little bit difficult to get. If we had 10 or 12 different satellites that we wanted to identify, it would be difficult to identify them each uniquely from each other. Where one other system that can do that quite well is called augmented reality, or AR tag. And that's basically just a black rectangle with an inside of that a grid of black and white squares or pixels. And then based on we know how large that grid is supposed to be, and then we know that each ID, each individual tag has its own subset of pixels in there, then we can determine uniquely which tag is which. So we can identify which face of a CubeSat we're looking at. We can identify which CubeSat we're looking at in general, which is quite powerful. And these systems can also be quite accurate. We've done some testing where we've been using a Raspberry Pi camera attached to a Raspberry Pi at a couple different camera resolutions, 640 by 480, 960 by 720, and 1280 by 960. And so for measuring in about the 0 to 3 meters range, so this is just a single degree of freedom, we get much better results with the higher resolution camera. This would be expected. That's just going to require a little bit more processing at the same frame rate than the other camera. But if we just look in the 0 to 1 meter range for distance, then we can see that there's some linear offset for each one of these. Now that just might be slight calibration inconsistencies or imperfect tag size. Either way, we can turn a 1.5 centimeter error after we linearize it out to a plus or minus 0.5 centimeter error on just distance, which is incredible. But we also did some testing, a little bit more realistic, where we have not just 1 degree of freedom, but we've got a 3D translation and a little bit of rotation there as well. So we had basically 2 laptops displaying tags and then 1 stationary tag. And then we would take an estimate of the relative position of all 3 of these with each camera, and then fuse those together by averaging the distances between each, and then compare that to the true measured distance. So at the bottom left, we've got a MATLAB image of what this looks like to the computer. And then the position estimates are not perfect as of yet. In test 2, they're off by as much as about 12 centimeters, which is not ideal. But I think we really just need more testing here and try to get more testing in a motion capture volume. But it at least works, and it translates decently well, still a lot better than GPS or similar cost solutions. But now we can talk about the dynamics and control. So the model we're using here was derived by Hide in his 2012 paper at the bottom of the slide. And basically this model has a 6-element state vector where we've got our XYZ position and our XYZ velocity. This model is linearized about a circular orbit about any body. So what we're using Earth as our body. So we use mu, the standard gravitational parameter of Earth, and then the other parameter is the radius above the body which we're orbiting. So we've been using a 100-kilometer orbit, which is about the altitude of the ISS, for that total of 6,500 kilometers from the center of the Earth. So that's for a single agent. If we wanted to extend this to multiple agents, it's quite simple. Since multiple CubeSats orbiting about Earth are not going to affect each other unless they are thrusting directly at each other, there's going to be no noticeable effect. There's no correlation between one CubeSat and the other. So we can just stack their state vectors together and then create an identity block matrix of zeros and then the A0 matrix we have for each agent, because they're all disconnected. And then now that we have our linear model for 3 different CubeSats, we also defined a PD controller. We didn't try PID because the integral term is only for steady state error, and that's not the biggest concern right now. And also the integral term tends to add a lot of oscillation to the system and a lot of sort of needless waste of thrust, which on a CubeSat is very critical, as you're only going to have a very limited supply of fuel for that. So we have a KP of -1 millionth, KD of -1,000th. These were just hand-tuned in MATLAB. Just trying to get the system to stabilize in one full orbit for about a 100-meter offset. And then we define this BK matrix as basically just translating the PD controller into state space. And then we've got our X minus our goal. So that now we can define a goal position that we would like the satellites to go to relative to one another. And then we can control them to get there. But first, let's talk about the nonlinear model and the linear model. The nonlinear model being just orbital dynamics in general, just to compare the two and make sure that they agree. So here we have the left plot is plotted in a 100 kilometer above Earth orbit, so 6,500 kilometers solar radius. And we can see that the equatorial orbit is perfect, it's great, that agrees perfectly. And then the other 2 orbits as well, with a little bit of inclination, are quite accurate as well. And then, so here in this right graph, we've got the blue is the Earth, and the orbit is plotted about the equator again. And then we've got, what we're going to have on the next plots as well, is these 5 points. So the circle, plus, diamond, square, and star. And these are going to be 1 point every 10,000 seconds, just to give an idea of how much time is passing on the plots at a time axis. So circle is 0, plus is 10,000, diamond is 20,000. And then so here we've got an example. So we've got CubeSat 1 started in a 100 kilometer orbit. We've got CubeSat 2 starting at an X offset of 100 meters. The CubeSat 3 is starting at minus 100X and plus 100Z. And they both have a goal position of 10 meters, minus 10 meters in X, and then plus or minus 10 meters in Y. And the uncontrolled system without a controller, the satellites just oscillate about it. They don't get closer or farther. They just stay away because there's no controller trying to bring them to the goal. The controlled system, however, does decay down to their goal positions quite well. We can see that they start accelerating there, and then they slow down as they get close. Now this slide is the same information as we had on the previous slide, just one-dimensional. It's a 3-dimensional. So we've got the X, Y, and Z position plotted versus time. So we can see that in the uncontrolled system, it just oscillates back and forth. And then the controlled system decays down to 0. The controller is able to bring the states down to their goal positions. And you might be wondering, how much thrust does this controller use? Well, so this is a PD controller designed to use as little thrust as possible. So the max thrust is only 100 micronewtons, which is easily attainable from really efficient ion propulsion. And even if that is maybe a little bit high, it is only for the first 30 seconds where the satellite's accelerating, towards its goal position, and then it slows down and has to turn around and thrust the opposite direction to try to slow down because there's no friction in space. So you've got to cancel all of your momentum. So let's talk about distributed state estimation. So a distributed state estimator, as opposed to a centralized estimator. Centralized estimator is where we would have each agent take its measurements and then send them all to a central controller that would then try to estimate the best position of the swarm and then send that estimate back to each agent so that they would know its position. This works great if you have, if each agent can talk to the centralized estimator. It works great. It's very low compute because you've only got one agent actually computing the state of the whole swarm. But if you have a situation where not every agent can communicate with every other agent, then you could have a problem where some of the agents just don't get an estimate at all, and then they have no idea where they are. Whereas if we have each agent be distributed, so each agent makes its own estimation of where the other agents are, that it can see the obstacles, and then just send that to its neighbors, we can have each agent have sort of the idea of what its neighbors can see and get a much better estimation and get an actual estimation without having to connect to the centralized estimator. This can also be a benefit if we want to take a big group of agents and then split it into two, whereas if we had a centralized system, we would have to tell each satellite which centralized controller to try to send data to and listen to, whereas a distributed system, we can just separate them out and then they'll just listen to their neighbors and it'll work great. One of the nice things about this distributed state estimator invented by Amir Tamjidi is that it's just as accurate as a centralized estimator if there's no link failure. So you're not losing accuracy by using this in the long run. So to test this and look at it, we designed a very simple test. So we just have two single state agents, so almost like we've got two balls rolling down a one-dimensional ruler. And each ball is moving at a different velocity. So we can see the states increasing in this plot. Agent 1 is moving at 1 meter per second, agent 2 is moving at 2 meters per second. And yeah, the A and B matrices are basically the simplest system we could come up with. And then here we're going to plot the error. So there was some measurement error with the system. And then, so we've got a centralized and a distributed estimator. So this test we had for the first time step, the system is fully connected. The agents can talk to each other, so the centralized estimator and the distributed estimator completely agree. Then the second and third time steps, the system cannot talk to each other, so the estimates aren't perfect anymore. But then the third, the fourth, and fifth time step, the system is reconnected again. So the distributed estimator can use its advantage of having the agents talk to each other and try to minimize that measurement error and try to take the offset that when the agent disappeared, you assumed it was just going to continue on its path. Then there was some error there, so then we can try to minimize that after we reconnect again. So we can see that the distributed estimators have a lower error right after that, and the centralized estimator is a little bit higher. So the distributed estimator functions better when there's some probability of link failure. We can also look at the distributed estimator itself. So we can look at it, the accuracy over the consensus steps. So the first measurement, this yellow and blue lines down here are both agent's estimate of the position, the state of agent 1. So we can see that there's some measurement error there and that they disagree. But then as they communicate their measurements with each other, then they each come down to the same final answer and agree on that. And then for the disconnected steps 2 and 3, they cannot talk to each other. But then in step 4, they then communicate and agree again on a better estimate of the whole swarm. So that we talked about all the things that we've done in the paper, all the things that we're doing with other papers as well. Let's talk about what we're going to do this summer and in the next year. So one of the things we're going to try to do is try to get better measurements of the position-based pose estimation. So we have a motion capture volume in one of the labs, and we're going to try to use that to get really accurate position and orientation measurements to compare these two to see how accurate this pose estimation is. We're also going to try to, currently it's all just been, we set the tag on a table and take a measurement. We're going to try to implement this on a set of robots or a quadcopter that just follows tag around to try to get a little bit more real-time operation as well. We're also going to try to implement this distributed state estimation method on this platform called OpenMAS, which is a free GitHub. It's actually pretty nice to use. We're going to test that on different systems. We test it on CubeSats. We can test it on quadcopters. Really, any model we can test it on. Then we're also going to try to test it on different link failure probabilities. So how does this compare to a centralized estimator? 10%, 20% link failure. How does it continue to be accurate with worse and worse sensors? Then we're also going to address some of the review comments that we've already had. So one of them was to try to compare this linearized model to the closely Wiltshire equations. So we've already compared this to the nonlinear true dynamics, but we can compare that to this as well to just see how it compares to the state of the art and what the differences are there. I think it's a great idea. And then another thing is to test a different orbit radii, because as mentioned, the 100-kilometer orbit that we're using, which is the same as the ISS, is a very, very low orbit in terms of the full scale of things. The ISS has to be pushed up by specials every once in a while. That's not going to happen for CubeSats, so they're only going to last a month or a year there, which is not the best bang for your buck that you can get for launching a CubeSat. Then I'd like to acknowledge Dr. Ed Duke of the South Dakota NASA FCRAR project for funding, and then also just kind of helping us get this idea and being a great, nice guy. And then I would like to open up the floor for any questions that you may have.